Welcome to this S-Cubed tutorial, during which we will be talking about error analysis with special emphasis on physics experiments. The analysis of errors is crucial. Every quantity we present in our physics experiments has an error associated with it, and so it is very important that students familiarize themselves with the analysis of errors. Let's start with the difference between systematic errors and random errors. What are systematic errors? Systematic errors are biases in measurement, but they are biases in a predictable direction. For instance, if I have a micrometer screw gauge that gives me a reading of 1 millimeter when it should be reading 0, then my results will always be off by 1 millimeter. There will always be an extra 1 millimeter added on. This is an example of what we know as a zero error. The instrument does not read 0 and the quantity to be measured is 0. So as we can see, imperfect calibration of measuring instruments is a major source of systematic errors. And in this case, the systematic error would be constant. However, this is not true of all systematic errors. They are not necessarily constant, but they are usually a proportional or a percentage of the actual value of the measured quantity, meaning that it is nearly always possible to. There are several ways in which systematic errors can be reduced or at least detected. Firstly, by calibrating the instrument, and secondly, by checking the 0 reading not only at the start of the experiment, but also during the experiment, because this helps to detect drift. Another way of detecting a systematic error is by using the same instrument to measure a known quantity, a quantity whose value we know, and if we don't get that value, then we will be warned to look for a possible error. There is yet another way of detecting a systematic error, mainly by comparing the readings with readings made using a different apparatus. So basically you use an apparatus which you know to be more accurate, you measure the same quantity, and you compare the results. It is very important that measuring instruments such as ammeters and voltmeters are checked periodically against known standards. Finally, systematic errors can also be detected by performing experiments using different procedures and comparing results. It's not always possible to reduce the systematic error. However, if the magnitude and direction of the error is known, the accuracy can at least be improved by additive corrections or proportional corrections. Let's now turn to random errors. Random errors are unpredictable fluctuations in the measured data. Basically, the word random indicates that they are unpredictable. They are scattered on both sides of the actual value, meaning that, for instance, if the quantity I'm measuring should be 5, a random error gives me results which are both above 5 and below 5. The results would be scattered on both sides of the actual value. Therefore, the average would be the best estimate of the quantity, and in fact, that is how random errors can be reduced by averaging over a large number of observations, what we call repeated readings. Let's consider some examples of random errors. For instance, electronic noise in the circuit of an electrical instrument, fluctuations in room temperature. If the room temperature is 20 degrees and you're getting fluctuations both above 20 degrees and below 20 degrees, that's a random error. It's not a one-way bias like a systematic error would be. Other random errors include parallax errors, and many others. Basically, random errors often have a Gaussian normal distribution, and because of the fact that they are distributed both sides of the actual value as shown in the diagram, they can be evaluated statistically. But the best way, as we said, of reducing random errors is always to take repeated readings. Let's now turn to the actual mathematical analysis of an error. We'll be dealing with random errors because, as we said, systematic error cannot be analyzed statistically. For instance, if x naught is the measured value, then we shall call the error delta x. It is very, very important to bear in mind that delta x is always a positive quantity. We use plus or minus only when we're writing x naught in front, that is, we would write x naught plus or minus delta x on 2. In this case, we would mean that our error delta x is symmetrically divided before x naught and after x naught. Half of it is before x naught, therefore the plus delta x on 2, and the rest, the other half, is after x naught, therefore minus delta x on 2. But the plus and minus should always be used when you have x naught in front. Otherwise, the error is delta x and it's written as a positive quantity. If f of xy is a function of x and y, what is the total change in f due to changes in x and y? And the total change in f is written like this. The first term would be the total change in f. Next, we have the change in f due to a change in x only with y considered constant. You can think of it as if we're considering the total change in f is equal to the change in f per unit change in x times the total change in x plus the change in f per unit change in y times the total change in y. And that's the last term we have on the right hand side, which is this. Again, we're considering the change in f due to a change in y only with x considered constant. This can be generalized to 3 variables, for instance x, y and z, as shown here. Again, we have the total change, the change with respect to x, the change with respect to y, and the change with respect to z. In general, for a function f of n variables, we just add on the terms representing derivatives with respect to those variables, and we would have this general formula: df is equal to partial f by partial xi dxi. We do this for every variable xi and sum up. Let's take a look at some examples. We'll consider this equation, power equals current times voltage. I'm sure you're familiar with it. P equals IV. In this case, P is a function of I and V. So let's consider again a function f in terms of x and y. In this case, the total change in f would be given by this equation. We've already discussed this equation. So similarly, the total change in P will be given by, this is the total change in P, and it will be given by the change of P with respect to a change in I, plus the change of P with respect to a change in V. I is the current and V is the voltage. Now, from P equals IV, we can calculate partial P by partial I, which is partial differentiation, and it gives V, and partial P by partial V, which again it's simple partial differentiation, and it gives I. So, substituting in our equation, we get dP is equal to V di plus I dV. And this is what we get. Now, an important thing to note here, when we use dx, it's mathematically used to denote an infinitesimally small change. Now, physical quantities will not be infinitesimally small, they are finite. So we prefer to use delta x, the Greek letter delta, and so dp equals phi di plus I dv would become delta p is equal to phi delta I plus I delta v. Again, that's the voltage read off the voltmeter, that's the current read off the ammeter, and those are the total errors. The total error in the current, which is the readability error of the ammeter, and the total error of the voltage, which is the readability error of the voltmeter. Remember, we're talking about the total error. It's not plus or minus delta V on 2, it's delta V, the whole of it. So suppose we have the following table. There's the voltage in the first column, the current in the second column, and we've worked out the power in the third column. The uncertainty is written up here. If the uncertainty of if the readability error of the voltmeter is 0.02, up here we write plus or minus 0.01. Why is that? That's because what we're saying, remember we said we can only write the plus and minus when we have the actual value written in front. But here we do have the actual values, for instance 2.21, 3.05. So what we're saying is that we have 2.1 plus or minus 0.01. That is, our error of 0.02 is divided symmetrically before the 2.1 and after the 2.1. 0.01 before and 0.01 after, and therefore we get 2.21 plus or minus 0.01. The same holds for the current, which appears in the second column, and in the third column, as you can see, there's the power. Now, what is the uncertainty associated with the power? Let's see. Well, we know that the total error is delta p, and that in our table we've got to write plus minus delta p on 2. Now, from the previous slide, we get that delta p is equal to phi delta I plus I delta v. And as you can notice, the voltage and current are variables. In fact, there are 5 voltage values and 5 current values. The voltage and current are changing throughout the experiment, so which value of voltage and which value of current are we going to place here? The thing is that the error delta p changes with each value of voltage and current. Therefore, there is no constant delta p. Delta p is a variable. Another important thing to note is that, for instance, if the value of the current is 1.022 amps, we write it like this. Remember, there's this is half the uncertainty error. It means that the uncertainty error of 0.002 is divided, half of it before the 1.022 and half of it after the 1.022. Now, what I would like to point out here is that if we have 3 decimal places in the value that comes in front of the plus and minus, you've got to have 3 decimal places in the uncertainty. Why? Because, for instance, this 0 means that the uncertainty in the 1 is 0, while this 0 means that the uncertainty in that 0 over there is again 0. But this, so each number here gives the uncertainty in the corresponding number over here. So that's why if the value in front of the plus and minus is quoted to 3 decimal places, the error has got to be quoted to 3 decimal places as well. So this one over here means that the uncertainty in this is 1. In other words, the value 1.022 can vary between 1.023 and 1.021. It's plus 0.001 or minus 0.001. Let's consider some other examples. Magnification, which is image height on object height. Again, this means that m is a function of IH and OH. And the equation for f, when f is in terms of x and y, becomes delta m equals partial m by partial IH, delta IH, plus partial m by partial OH, delta OH. Now we can work out partial m by partial IH and partial m by partial OH from the equation at the top, this one, over here. So, do we just plug in these values and write delta m equals 1 all over OH delta IH minus IH all over OH squared delta OH? No, and we're going to see why. So, this is what we might have written. We're going to see why that would be wrong. If we write delta m like that, then remember we quote m with a plus or minus delta m on 2 after it. So, m plus or minus delta m on 2 would become like this. Look at the factor of 1/2 I've put in here. And that gives m plus the uncertainty or m minus the uncertainty. So we can write delta m is equal to 1 all over OH delta IH minus IH on OH squared delta OH, but we're claiming that this is wrong, and we're going to see why. So suppose we write delta m as it's written at the top here, then of course we would have to quote m with a plus minus delta m on 2 after it, and that would give m plus or minus all this. Notice that I've put in a factor of 1/2 in here. So that would give m plus the uncertainty or m minus the uncertainty. Now, as you can notice, the term in square brackets here is negative, so it decreases the error. However, if my errors are distributed on both sides of the value I read, which we shall call m0, that is, I've measured the value m0, and the errors are distributed on both sides of m0, as we've already discussed, plus delta OH on 2 in front, and minus delta OH on 2 after m0. The same holds for the image height, plus delta H on 2 in front, and minus delta H on 2 after m0. So we would expect that these errors would add up if my errors are distributed on both sides of the value I read, which we shall call m0. So there's m0 over there, and the error, the uncertainty, is divided plus delta OH on 2 in front of m0 minus delta OH on 2 after m0, and the same goes for the image height, plus delta IH on 2 in front and minus delta IH on 2. So we would expect that these errors would add up, that is, we would have m0 plus delta IH on 2 plus delta OH on 2 and m0 minus delta IH on 2 minus delta OH on 2. The reason is that if just because of this error minus delta OH on 2, my true value could be somewhere here, although I've measured m0, but because of the error, the exact value might be somewhere here. However, because of the error in IH, the exact value can also have an error starting from M0 that goes from M0 up till here. So if you add up those two errors, my value can be displaced from M0 by this much. And note that for the sake of simplicity, we remove the coefficients of plus delta IH on 2 and the rest, but now, of course, we have to put them back in. Thus, we write m plus or minus, all that, the terms enclosed in round brackets. And from now on, we shall modify our fundamental equation by putting in the modulus sign. The modulus sign means that we must always consider the positive values. That is, if partial f by partial y is negative, as was the case in the example we've just considered, we have got to take the positive value. We'll work out a few other examples. Let's consider Snell's law. So there you get the refractive index of the medium in which the incident ray travels, the angle of incidence, the refractive index of the medium in which the refracted ray travels, and the angle of refraction. Basically, we have a ray which is propagating through a medium, and at the boundary with another medium, it gets refracted. So I want to find error in eta I. Remember that eta I is the refractive index of the medium in which the incident ray is traveling. So now we'll work out a few other examples. Let's consider Snell's law. We have an eta I sine theta I equals eta f sine theta f. Eta I is the refractive index of the medium in which the incident ray is traveling. Theta I is the angle of incidence. Eta f is the refractive index of the medium in which the refracted ray is traveling. And theta f is the angle of refraction. Basically, we have a ray propagating through a medium, and at the boundary with another medium, it gets refracted. Now, suppose I want to find error in eta I. Remember, eta I is the refractive index of the medium in which the incident ray travels. What we've got to do first, this holds every time. If you want to find the error in a quantity x, first make x the subject of the formula. In this case, we've got to make eta I subject of the formula to get that equation. From this equation, it is clear that eta I is a function of three variables. We have eta f, we have theta f, and we have theta I. So, again, using the fundamental formula, we write delta eta I is the error in eta I due to the uncertainty in eta f, the error in eta I due to the uncertainty in theta I, and the error in eta I due to the uncertainty in theta f. It's like we're saying, this is the total change in eta I. This is the change in eta I per unit eta f times the total change in eta f, which would give the total change because of the error in eta f. And from the formula for eta I, we get that we can calculate partial eta I by partial theta I and partial eta I by partial theta f. We calculate that from this one here. Now, suppose that eta f is quoted in the lab sheet. That is, you've got a quoted value of eta f. That would mean that its uncertainty is 0. Even if it's not, the fact that it's quoted means that you should consider the error to be 0 because you yourself can't calculate it and can't find it out. So let's consider again this formula. It would become like this. Basically, the error in delta E the error in eta f has been put to 0. We substitute our previous results for partial eta I by partial theta I and partial eta I by partial theta f. Remember to take the positive values because of the modulus. And we get this. So the point here is when you have a constant, for instance, in this case we had eta f, but you can have any other constant. The first thing that you do is that you treat it like any other variable. In fact, we first extracted this term, partial eta I by partial theta f, delta theta f. We wrote this down, and then only later did we remove it. So first, write down the corresponding term in the error formula, and then later on just cross it out, just put the corresponding uncertainty, in this case delta theta f, to 0. This helps so as not to create confusion. Another important thing to note is that when I say a constant, bear in mind that it doesn't mean that if you have a constant, it's free of errors. So the thing to bear in mind is that when you have a constant, like for instance in this case we had eta f, the first thing to do is to treat it like you would any other variable and include its error term. For instance here we included partial eta I by partial theta f, delta theta f, and then just put in this case delta theta f to 0. You might ask, wouldn't it be easier to just not put in the term from the start? But as you will learn from experience, this procedure helps to avoid a lot of problems. So first, just treat the constant like a variable, include its error term in the formula, and then put delta theta f, in this case, to 0. Another important thing to bear in mind is that although I'm saying a constant here, it does not necessarily mean that a constant is free of errors. For instance, fundamental constants like Planck's constant and Newton's constant of gravitation, they have an uncertainty associated with them. What I mean when I say a quantity that has no error in this case, it's a quantity that either you're quoting it from a textbook and you're deciding to neglect its uncertainty. For instance, if you're using a Newton's constant of gravitation, errors from the experiment would probably be much more significant than the uncertainty in the constant, so you might choose to ignore it. Otherwise, it might be a constant associated with the apparatus, like the radius of something that you can't measure directly, and that's quoted in the lab sheet. In this case, since you can't measure it directly, you can't know the error associated with it. But when I say constant, it does not necessarily mean that there's no error associated with it. It just means, it just refers to those values which, for one reason or another, have 0 uncertainty, but not all constants are like this. So the uncertainty in the average of a quantity. Suppose I have a quantity x and I take 2 repeated readings. I tabulate my readings, and here there is plus or minus 0.001, so the instrument would have a readability error of 0.002. And what do I write over here? What's the uncertainty for x average? To find the interval in which the true value x lies, we use the following formula. So, this is a value from tables t, we'll see what that is later. We have n, which is the size of the sample. For instance, in this case, the size is 2 because we have 2 readings. And s. However, we won't be calculating the standard deviation. X average is the x value you have over here. And this is the true value of x. By true value, we mean the exact value, not the one you've recorded, but the one you weren't able to record because of the errors involved. So, let's have a look at this image. Here, each band has a width of 1 standard deviation. And if we compare this to the images shown previously, this image is from previous slides, where we had shown that when I say the error is delta x, it's like I'm measuring the dispersion of my data points around the true value. The true value would be in the middle here. And this would be delta x, the total error. Now, if we compare these two images, we can see that instead of the standard deviation, we can use delta x on 2. Thus, we can write the formula that we presented initially, which was this one, like this. Note that we've replaced the standard deviation with delta x on 2. And this, therefore, should be multiplied by 2 to get a total error. Remember, the plus or minus means I'm dividing the total error into 2, half before the actual value and half after the actual value. So the total error is written as t delta x on root n. We can get the value of t from standard tables. That's the sample size. In this case, we would have to use n equals 2. The subscript 0.025 tells us that we are 95% confident that the true x lies in the range we've specified. We can get the value of t from standard tables. N would be, as we've said, the sample size. In this case, it would be 2. And this is the corresponding t. In this case, it's 12.706. The 0.025 tells us that we are 95% confident that the true x lies in the specified range, that is, in the error range we've calculated. If you want a different confidence interval, you can use a standard textbook to look up the t-distribution table. That distribution is known as the t-distribution or the student's t-distribution. When doing error analysis, it's important that you conclude by working out the accuracy and percentage error. The accuracy gives us our experimental value as a percentage of the actual value quoted in the literature. That is, you can't always calculate the accuracy. If you don't know the quoted value, you can't work out the accuracy. The accuracy is worked out like that. But if your experimental value happens to be greater than the quoted value, of course this would be greater than 1 and you'd get an accuracy that exceeds 100%, and that wouldn't make sense. So in this case, just put the quoted value as numerator and the experimental value as denominator. Now, the percentage error tells us what percentage of the experimental value amounts to the uncertainty. It gives us our uncertainty as a percentage of the value, not the quoted value in the literature, but the value we have found. So we get the error as a percentage of the value we found in our experiment. And this is the formula we use. This is some bibliography. And that's all for today. I hope you will find this presentation useful, and I hope it will help you in your error analysis.